Hello everyone, so welcome to lecture 34. So today we will take a deep dive into some introduction to statistical mechanics. So far we have been looking at thermodynamics, we have been seeing how the equilibrium properties come as curvatures of certain thermodynamic quantities. We described it, so we tried to find a physical meaning to these properties. We said these properties are actually, you take away the system away from equilibrium, how these properties determine what is a restoring force like thing that will bring back the system towards equilibrium, right. But so more than that, thermodynamics does not give many more insights. Thermodynamics is good for calculations, right, but if I really want to know what is happening at a microscopic scale, I need to go to I need to understand statistical mechanics. Okay, so like I always keep saying, statistical mechanics, although it came later in chronology, thermodynamics is a science that came before statistical mechanics. Stat mech actually explains the microscopic picture of certain things that seem empirical in thermodynamics. For example, entropy is a quantity we just assume to exist in thermodynamics. Entropy is some sort of so there are definitions of entropy, which is so if I say entropy is just delta Q reversible by T, right. So this is dependent on a path, it is dependent on a so a reversible process. I have to define a reversible process, I have to look at the delta Q, and then that by T is defined as delta T in thermodynamics. But statistical mechanics actually gives you a more fundamental definition of entropy, for example, right. So entropy is actually so this is the famous Boltzmann distribution, Boltzmann definition, which says that S equal to K ln omega. And K ln W, where W is the total number of what are called microstates. So there is a microscopic picture that goes into this problem, and K is just a Boltzmann constant. So you just count the number of states, the logarithm of the number of states, number of microstates in any system, right. So we will actually define what microstates and macrostates are today, is your entropy, right. So it gives me a physical picture of okay, so where all can the system live, right. So in what all states can the system stay. So I will count all possible number of states and then say that the entropy is all possible number of states, or logarithm of that, right. Now if I increase the number of states, so there is more freedom for the system to exist in more number of states, and the entropy increases, right. So statistical mechanics gives a meaning to what a quantity like entropy is. Thermodynamics just says, okay, so just shut up and calculate. You have a reversible process, and this reversible process has a delta Q associated with it. There is some heat input, there is a heat output from the system and to the system, and so I understand that to be delta Q, and the delta Q by T is my entropy. Okay, so so there is a difference, right. So you go deeper into thermodynamics, there is statistical mechanics, but so statistical mechanics describes the microscopic properties, the microscopic nature of various systems. It will be more clear as we keep doing more as we go through this class. But thermodynamics starts at a certain stage where you assume that entropy exists, you assume that temperature exists, and all these things. Okay, so so today we will look at statistical mechanics and what quantities in statistical mechanics actually go and connect towards this bulk thermodynamics that we have done. And based on that, so we will look at what properties means from a statistical mechanics framework, what equilibrium properties mean from a statistical mechanics framework. Okay, so okay, so first, when we do before I actually begin, so this is the book I will follow very briefly, right. So there is chapter 4 here, which I'll try to use. So this is called Introductory Statistical Mechanics, and this is written by Roger Bowley and Mariana Sanchez, right. So these are the authors of the book. I am following the second edition, but so this is well written and useful for beginners especially. Okay, so so I so I have a system, and this system has many so this is, let's say it's a so when I talk about energy states, right, so something that comes to my mind is a quantum mechanical system, right. But so it does not need to be quantum mechanical, even classical mechanics, so a system can exist in several different energy states. Okay. So there are so several independent particles, let us say. Each of these particles can have different energy, right. They can exist in different states. States are not necessarily just qualified by their energy, but a state can typically quantified by its momentum and energy, right. So both of them together quantify a state for me, right. So this is like an eigenstate in quantum mechanics. Okay. So stat mech, so I do not really care about what is the nature of the state. I just need to know if these are so which particle has what energy and so on and so forth, right. So I am going to say that here is my system has all these energy levels, right. So this is energy 0, this is energy 1, this is some energy 2, this is energy 3, and so on and so forth, right. So what I am drawing here is so there is state 1, state 2 and state 3. So the degeneracy of energy 0 G is actually 3, G not equal to 3, G1 equal to 2, right. So G2 equal to 3, G3 equal to 1, right. So G is actually what is called the degeneracy, which means several states can have the same energy, or energy degeneracy, right. So which means that several distinct states, distinct means classically each of these states, the particle can have different momentum in each of these states, right. Quantum mechanically the wave function is different. Okay. So several or so the wave vector is different, right. So it is the same thing, right. Several distinct states have the same energy. Okay. So now I have such a system, and in such a system I am going to fill n particles, right. So n independent particles, that means these particles are not interacting with each other, independent non interacting particles. Okay. Now I can put so let me say that I have what are called distinguishable particles. And I have let us say 6 of them. Okay. So if I have 6 distinguishable particles, I am going to use 6 colors to represent them. So let me put 2 particles here in this state. Let me put so a third particle here. Okay. So let me use a different color. Let me put a third particle here. Sorry. Let me put a fourth particle here, let me put a fifth particle here. Okay, so that color is not very visible, so let me use a pink color. Let me put a fifth particle here, sorry, and let me put a sixth particle here, right, or right there. Okay. So I mean, okay, so here I am assuming that one state can take many particles, right. So a sixth particle here. Okay. So this is sort of how I distribute these particles, right. Now I am going to say I am going to fix the number of particles and the total energy is fixed. Okay. So total energy is, what is the total energy? So if there are n1 particles here, n2 particles here, n3 particles here, n4 particles here, total energy is sigma ni epsilon I, right. So that is the total energy, that is fixed, and the number of particles, which is sigma ni, is also fixed. Okay. So now we will not go into the statistics of this particular problem, but this is so I am just this is to illustrate the terminology in stat mech. So essentially what I have is since so I come from IISc, let us look at so where ISc graduates, they can be bachelors in science or MTechs or masters in science, whatever be the degree, it is a bachelor or master's degree, where are they getting placed? Okay. So, that is an analogy I want to make here, and what is the salary, right. So, salary determines something like the energy state, right. So, let us say there is a lease salary, this is rupees 0 per annum per month, or this is bankrupt essentially, right. Okay. So, immediately after you graduate, how many people do not have any jobs, how many people go bankrupt, right. So, that is the ground state, or that is the 0 energy state, right. So, the 0 salary state. Then let us say I have a state where I have some degeneracy, right. So, for example, there are students who want to pursue their passion, and passion does not pay much nowadays, right. So, this is some passion job. This is okay. Some people want to pursue PhD, right. PhD also does not pay much nowadays, right. So, this is some rupees 30,000 per month, right. So, these are degenerate jobs in the sense that they both have the same salary or similar salary, but they are different jobs, right. So, that is different states, but the same energy. Okay. Then let us say there is rupees 80k per month, okay, and that is so let us say there is a government job or a startup. I just started something, or I joined a startup, there is a PSU and so on and so forth, right. So, that let us say that pays something more, right. So there is some degeneracy there, right. So, all these are various jobs, right. It can be many more, right. So, I am just giving you an example. Then so let us say there is rupees 1 or 1.1 lakh per month, right. So, this is what one of my students who worked in Tata Steel told me, that he was paid 1.1 lakhs. So, Tata Steel, right. So, some sort of a private job, right. So, but it is a tech job, tech job 1, tech job 2 and so on and so forth. There is some degeneracy there, right. Then there is rupees 4 lakh per month, which is some sort of so the other software, okay, not when you start, but probably you can land up in some jobs such as in Google, Amazon, Microsoft, all these sort of companies. Well, you can earn more, right. So even when you start, if you are a good student, right. Okay, then there is jobs. Okay, so these are just numbers that I made up, right. So don't quote me on this saying that, oh no, I got a job in Google, but they are not giving me 4 lakh per month. Okay, so so then you have so something like 10 lakh per month, where you are looking at people in finance job 1, people doing so Google, Microsoft, these are the ordinary software sort of jobs. But if I am nowadays building robots, doing AI, etc., so I have jobs that are more higher paying, right. So finance 1, finance 2, right. So and so on and so forth, or so I do some MLAI and build my own chatbots and whatnot. The ChatGPT, I am a builder of new transformers and all these things that are coming up, right. So then I get paid much more, right. So per month. Okay, so now these are the various states that exist. Now I am going to fill. So I have roll numbers 1 to 100, or let us say 1 to 100, right. So I am going to fill in bankrupt roll number 1, roll number 5, roll number 100, do not have jobs yet, right. Passion job, there will be always people who are passionate about certain things, right. So there is roll number 2, roll number 9, roll number 17 are passionate about their jobs. PhDs, okay, there are some people who are crazy enough to do PhDs nowadays, some people like me, for example. So let's say roll number 7, roll number 17, roll number 27, whatnot, right. So I start filling up government jobs. There are some people who take government jobs who are happy that they have a secure job, right. So that would be roll number 8, roll number some 16, roll number whatever, right. So and so on and so forth, right. Okay, so now based on this, right. So this is essentially my particle filling, right. So here each of my ISc graduate is a particle, analog of an independent particle, and each of them are what are called distinct particles, right. So not indistinguishable particles. All ISc people, all ISc graduates are different. They have their own identity, right. They are not like electrons. Electrons are indistinguishable, but ISc graduates are distinguishable, or these gas molecules in a room are distinguishable, right, and so on and so forth, right. So you can fill this up, and you can so this will be here this is one ensemble, right. So what I define now is one ensemble, but it is perfectly possible, right, given a different circumstance of things, that so I can have a different ensemble, a second ensemble, where roll number so the second ensemble I am going to write it in green. Roll number 2, roll number 7 become bankrupt now, right. Roll number 7 is no longer pursuing a PhD, right. So in a parallel universe, so this is what is happening. Roll number 4, some 22, 37 become PhD students, and so on and so forth. Some roll number 55 takes a finance job. Roll number so roll number 71, 77, 79 etc. take a Google job. Roll number something else takes a Microsoft job, and so on and so forth, right. So there can be multiple what are called ensembles, right, that you can create from all the particles, or in this case graduate, occupying different states. Okay. Now, if I fix the energy of the system, if I fix and the number of particles in the system, some microscopic particles, right. So what are these particles exactly becomes clear when we actually do problems with respect to spins and polarizations and everything that is related to our properties. But as of now, just assume that there are these particles which are gas molecules or graduates or electrons or whatever they are, right. So if I fix the energy of the system and the number of particles, right. So the U is fixed, that is the total energy of the system, and the number of particles n is fixed, then such ensembles are what are called microcanonical ensembles, right. So there is no transfer of energy, there is no sharing and caring of energy between the system and the surroundings, right. So there is no transport of particles between the system and surrounding, and so on and so forth, right. So these ensembles are called microcanonical ensembles. Okay. Now and so in thermodynamics you may have studied this as just closed systems, right. So StatMech has a different nomenclature, you call it microcanonical ensemble, a big name, but essentially what this means is that it is a closed system. Okay. So all right, now let us get back to our problem of different energies, right. So epsilon 0, epsilon 1, epsilon 2, something like that, right, and I am filling up particles, right. So I am filling up this color here, I am filling up this color, so this is a different color, yes, okay, good, and this color here, and I am I am just filling up pink here and I am leaving this empty, let us say. Okay, so there are no particles there, right, or also green. Okay, so 1, 2, 3, 4, 5, 6, 7. So I have n equal to 7, and I have total energy equal to E, right. So these two I conserve, right. So I fix them. Okay. Now a microstate defines for me the address of every particle in every state. Okay, complete string of this entire thing, right. So okay, this is also pink. I will use a different color here. And so let me use blue. Okay. So I have 7 different particles, right. So of different colors, and so of an energy which is supposed to be 2 E naught plus 3 E1 plus 2 E2. This is going to be my total energy. This is fixed. Okay, and I have n equal to 7. This is fixed, right. So one of the microstates is what I have shown you here. So one microstate is shown in figure 1. Okay. Now let me draw another microstate, right. So now this time I am just going to say okay, so these two, the blue particle will be here. Okay. So then I just put the pink here, the other blue here, right, and the pink here, yeah, that is okay. Then so I am going to exchange these things, right. So I will put this one here, this one will be here, this one will be here, and or the other way around. And black is in the middle. Okay. This is another microstate, same energy. And same number of particles. Okay. So so these are so it describes me the complete address. The pink particle is sitting in ground state of state 1. The green particle is sitting in an energy state of E1, which is, and the first degenerate state of that, right. So if I give you the complete trajectory or complete details of every particle, that defines for me a microstate, right. So that is a microstate in a system, right. Now you can also say, okay, so what about there is something called the macrostate, right. Now macrostate, so here I am going to tell you that so energy of E1 has particles N1 equal to 2, energy E0, N0 equal to 2, energy of E1 has particles N1 equal to 3, energy of E2 has particles N2 equal to 2, right. So essentially the string of numbers 2, 3, 2 in energies E0, E1, E2, this defines for me a macrostate. I do not really care which particle comes and sits here. This can be a black particle, this can be a blue particle, I do not care, right. So it could be a different microstate, but it all belongs to the same macrostate, right. So okay, so let me completely change this. So this is black, right, and the pink goes and sits on the top, right. So this is pink, right. So, that is a different microstate. I do not care, right, but the macrostate is exactly the same. This guy and this guy have exactly the same macrostate, right. A macrostate can have multiple microstates, right. So, these two for example belong to the same microstate, sorry, belong to the same macrostate, but they are different microstates, right. Microstate gives me address of everything, macrostate just looks at the state at a coarser energy level, right. So, energy 1 has how many particles in it, energy 2 has how many particles in it, that is what it asks, right. So, it does not care which particle is sitting in which energy level, etc. Okay. So, yeah, so that is the difference between a microstate and a macrostate, right. Now, so if I have something like so I spoke about these are all indistinguishable particles where each particle has a different color. If I sorry, these are all distinguishable particles. If I look at indistinguishable particles, then okay, so then I mean, so if I am going to just draw, so I will draw everything in one color. So, this is let us say one macrostate, it is the same macrostate, but two different microstates, right. But so exchanging this particle with this particle, right. So, exchanging these two particles would have yielded, so these are indistinguishable. So, they are the same microstate, right. So, exchange of particles would lead to the same microstate. Okay. So, they are not different microstates for indistinguishable particles, but if they are distinguishable particles, if this is green, right, and this is yellow or something like that, then exchanging these two particles will yield. But if they are remember that if they are distinguishable, it will yield different microstates. Okay. Since they are indistinguishable, the exchange of particles will lead you to the same microstate. But so this is microstate 1, this is microstate 2, 1 and 2 have the same macrostate. Okay. So that is just so what people mean by microstates and macrostates. So if the definition is clear, then so every state, right. So you will see that people call it an eigenstate, so which is an independent state, this state is independent of this and so on and so forth. It can be a quantum mechanical eigenstate, it does not need to be, all you mean is this is an independent state with respect to the other states. Okay. So for example, this state I am going to call it an eigenstate. Okay. So you will hear all this terminology in StatMech. Okay. So now, why are we talking about all these things? Because the fundamental postulate of statistical mechanics so that says all microstates are equally probable. Okay. So whether I have this microstate has the exact same probability as this microstate occurring, right. So every individual microstate has an equal probability. Okay. So this has a probability of occurrence of 1 by capital N, where capital N or capital W, let me just write W, is the total number of microstates. This has 1 by capital W, where W is the total number of microstates. You remember what W is? W is what Boltzmann had used, right. So W is the total number of microstates. Now we can actually quantify this by we can actually qualify this by saying total number of accessible microstates. Okay. So, sometimes some certain microstates exist, but they are not accessible to my system, so I do not consider them, right. So that is what this is. Okay. Now, let us look at a very simple example. Okay. Now, the simple example is I have I have what is called an Ising system, where I have a lattice, right, of let us say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 positions, right, and each of these 10 positions has spins on them, right. So, I have n equal to 10, right. So, I have 10 spins. Okay. So, each of them can be 3, 4, 5, 6, 7, 8, 9, 10. So, these are just the spatial positions, right. So, this is position 1, this is position 2, these are like roll numbers of my ISc graduates, right, 1 to 100. This is 1 roll number, 2 roll number 3, roll number 4, position number 5, 6, 7, 8, 9 and 10, right. So, in some sense I am talking about a problem where I have distinct particles, right, or distinct spins, right. So, 10 spins which are all distinguishable. Okay. Now, so n equal to 10 I fix that, right. Now, let us say so all these spins are seeing a spin can either be up or down. A spin can exist in either up state or down state, right. Now, depending on the energy of this system, right, so which also I am going to fix, right. So, let us say there is all this lattice is seeing a magnetic field B, right. So, if this is seeing a magnetic field B, a spin up will have an energy of minus mu B, a spin down will have an energy of mu B, where mu is just a Bohr magneton, right. Sorry, mu is the magnetization. So, mu dot B it will be and it is in Bohr magnetons, right. So, this is plus mu dot B, that is minus mu dot B. Okay. So, this is the energy of the spin up and this is the energy of the spin down. Okay. So, I essentially so every spin can be in either spin up state or spin down state. Okay. So, I have 2 energy states, right. So, epsilon equal to minus, so I am just going to call this minus E1 and this I am going to call it minus E2. So, I have minus E1 and minus minus E1 and plus E1. Okay. So, essentially I have a system which is just which has a 2 level system, right. So, this is what is called a 2 level system, easy to understand, no degeneracy, nothing, right. So, this has an energy E1, this has an energy minus E1, this has an energy plus E1. Okay. And so and I have to put 10 particles in this, 10 distinguishable particles, or spins in this system. Okay. So, now I am going to tell something else, that the energy of this system is fixed, it is actually 0. Okay. So, if energy is 0, the only way energy can be 0 is if I have 5 up spins and 5 down spins. So, n is fixed, n equal to 10, E equal to 0, which means I am actually saying that my E1 should have 5 spins and my E2 should have 5 spins. So, this is in E1, this is in E2. Okay. So, similarly you can have n different spins and E is the energy. So, what you are saying is, okay, so n1 plus n2 equal to n, where n1 is the number of particles in energy state 1 and n2 is the number of particles in energy state 2, right. So, this is E1 and E2, or minus E1 and minus E2, right. and or let us write n minus 1 and n 1, right. So, that way we get minus E 1 and plus E 1. Okay. And n minus 1 number of particles E minus 1 minus E 1 plus n minus, okay. So, since I am generalizing, let me not write it this way. So, I have I have two level system. Let me just write it nicely and normally. So, I have a 2 level system with E 1 and E 2, two different energies, right. E is the total energy. So, I have n 1 plus n 2 equal to capital N, and n 1 E 1 plus n 2 E 2 equal to capital E, and that means that so I have two equations, two unknowns, and these unknowns are n 1 and n 2, and so I exactly know what n 1 and n 2 are. N 1 and n 2 are exactly known. Right. So, I have one macrostate in this system, right, where E 1 has n 1 spins and E 2 has n 2 spins, right. Okay. Total energy is fixed, capital E equal to 0, and total n is fixed, that is n 1 plus n 2 ideally. Okay. Now, I ask the question, how many different microstates are there? Okay. Now, all right. So, essentially so in my 10 1 2 3 4 5 6 7 8 9 10, right, I need to have 5 up spins 1 2 3 4 5, and I need to have 5 down spins 1 2 3 4 5. That is microstate number 1. Okay. Then microstate mu st. Okay. So, then I can have another configuration where I have 3 4 5 6 7 8 9 10. So, I have 1 2 3 4 5 up, and then I have 5 down, right. So, this is another microstate mu state 2, and so on and so forth, right. So, now if I keep doing this exercise so I can do it forever, but I want to count how many number of such microstates are there, and that is an easy thing because I have n 1 plus n 2 particles, and so I need to put n 1 in, so total number of microstates is, I need to put n 1 in state E 1, and I need to put n 2 in state E 2. So, the total number of ways I can do this from elementary combinatorics is just n c n 1, right. So, which is so which is this quantity, right. So, in case of 10 particles and 5 up 5 down, the total number of ways of doing this is so W equal to 10 factorial by 5 factorial times 5 factorial, and what is that number, or 10 C 5, right. So, that is so that is how it is denoted, and this number is actually 252, total number of states, right. So, I have a magnetic system with various spins, right. So, all these are independent spins. Okay. So, and then I put in the condition that so the total spin total energy of this system should be 0, which means the number of up spins should be the same as number of down spins. Down spins have a negative energy compared to the up spins, right. So, total energy adds up independently, and so that, and the total number of spins are constant, right. So, based on that I know the total number of microstates in the system, right. Now, if I have total number of microstates, I know what the entropy is. Entropy is just k ln omega, in this case k ln 252, which is not a big number to calculate, right. But typically so these values are quite large, right. So, the number of particles will be something like 10 power 23 Avogadro number, right. And so so the everything scales up quite large, right. So W will be huge, right. In real systems W is like 10 power 23 power well. So it is a large number, that is why you know. So if you do a logarithm of W, I will exactly tell you what the number is very soon, but if you look at the logarithm of W, you know, so that becomes a bearable, you know, calculable number, right. So actually it is something like 10 power 23. So that is the magnitude of W, right. So in real systems with Avogadro number of particles and so on and so forth. Okay. So but you know, you can actually show, I am not going to show that here in this class, but you can actually show that if I actually look at log omega, log W rather. So if I am actually looking at log W, log W will come out to be, you know, something like n1 by n1 plus n2 with some approximation, of course, you know, log n1 by n1 plus n2 plus n2 by n1 plus n2 log n2 by n1 plus n2, right, and k log omega is just k times this. So that is your entropy, or that is you know, roughly k times P1 log P1 plus P2 log P2, right, where P1 is the probability that the system is in state a particle, right, or a location, right. So here in my you know, Ising system, I say, okay, so what is the probability that this is either up or down, right. So that this is up has a probability P1 and this is down has a probability P2, right. So now you know, so in this case, right, so I have 5 up and 5 down, right. So that this is up is you know, so that, you know, position A, let me name it A, has a spin up is half probability, right. So P1 is half and position A has down spin is P equal to so P2 equal to half, right. So half probability, but in general it does not need to be, it is you know, so if I have n1 particles of spin up and n2 particles of spin down, that position A has spin up is n1 by n1 plus n2 and position B has spin position A has spin down is the 1 minus of that, or n2 by n1 plus n2. Okay. So so this is a standard you know, so even for a mic okay. So what we did so far was we fixed N and we fixed E. So the system that we looked at is what is called a microcanonical ensemble, right. So in which, you know, we calculated the entropy of an Ising system with n equal to 10. So with n you know, particles, and E1 and E2 are the and E is the total energy split as E1 and E2. Okay. So S is, you know, you can write S as k ln omega, which will actually turn out as k P1 log P1 plus P2 log P2. Okay. All right. So with that, you know, so we will stop it here, right. So this is a very simple example of using StatMech, right. So I just took a you know, an Ising system with two level Ising system, right. So and then explain to you what a macrostate is, what microstates are, and you know, all these microstates. So what is the probability that I get a microstate that I have shown here, right. So the probability of getting this microstate, right. So once you know, so you define these constraints, the constraints are defined E equal to 0, n equal to n, E equal to 0, n equal to 10, right. So at E equal to 0, n equal to 10, I take a snapshot of my system, and then, you know, so what is the probability that I see this state when I take a snapshot of my system? The probability is 1 by 252. What is the probability that I see this state? The probability is 1 by 252. Like that, any of the 252 states, if I isolate it, if I take a snapshot at a given instant and then observe that, right. So, the probability of observing that system is 1 by 252, that microstate is 1 by 252. Okay. So, if I do this experiment some many times, right. So, I will equally populate all the microstates. So, that is an ensemble so experiment. If I create several ensembles of this, right. So, something like 252 is the number of states. So, I will create some 252 million such ensembles. Then so I will equally populate all the microstates. So, all the microstates are so I would have seen microstate 1 to 252 million times divided by 252 1 million times. I would have seen microstate 2 about 1 million times, and so on and so forth. There is always going to be some fluctuation, but as I keep increasing the number of my experiments, these fluctuations also tend to reduce, right. So, okay. So that's essentially that's giving you a feel of statistical mechanics, but these are the so this is how we deal with what are called microcanonical ensembles. Okay. So, today we looked at some basic language of StatMech, right. So in the next class we will implement this in what are called canonical systems, or closed systems in thermodynamics language. And then we will actually go to see how the StatMech is really related to thermodynamics, okay, and the properties. Of course, we have to get to properties as soon as possible, right. So, probably in the next class itself we will be able to get to the properties, okay. And so what is the microscopic? So, here you saw that so I am worried about every little spin, right. So, the microstate is worried about every little spin in every position, right. Thermodynamics does not care about that. Thermodynamics tells me that okay, the net magnetization here is 0. Right. So, that is what thermodynamics is telling me, but StatMech is telling me no, it is 0, that is okay, but there are several microstates through which there are 252 different microstates through which I can get this magnetization of 0. Okay. So, StatMech is going into more sort of microscopic picture, whereas thermodynamics does not, right. So, but something would relate this microscopic picture to a more macroscopic quantities, and that is what we will try to see in the next class by looking at slightly expanding the problem towards closed systems, okay. So, or canonical ensembles. Okay. So, with that we will end here, and we will meet you again in the next class. I will meet you again in the next class. Thank you.